Vale. O si prefieres para estar aquí quieto, como tú.
Yo no estoy quieto, es un bicho inquieto.
Sí, igual es, pues nada, plan, sí que póntelo así más o menos.
Intento
Hola,
tener...
hola. Sí, porque si te lo alejan mucho...
Vale. Ok. Hola. Sí, vale. Que para la presentación básicamente eran 90 minutos, ¿no? O sea, es el slot entero. No creo que lo haga porque, bueno, también para dejar...
De hecho, ayer unos speakers dijeron, vamos a parar 10 minutos.
Vale. O sea, yo pensaba hacer como 1 hora y 10, algo así, y luego ya dejarlo, porque si no me parece un poco killer, ¿no? Sobre todo empezar así.
De hecho, también como que la gente hacía quizás media hora y habían preguntas en medio de
Vale, también eso, ¿no? Eso te iba a preguntar, vale.
Como que hacían media hora y decía, bueno, hasta aquí alguna pregunta.
Ok.
Sí, pero vamos, si acabas hay 10.
Vale, fenomenal.
También si quieres hacer
Un break, ¿no? Me ha dicho... Sí, o sea, yo pensaba lo que le estaba diciendo, hablas o sea, 1 hora y media, ¿no? Porque es mucho también para dejar tiempo para preguntas, entonces pensaba 1 hora y 10, 1 hora y cuarto. Entonces, bueno, según vaya, igual puedo preguntar si queréis hacer... Bueno, tú también me dices, si es que la gente está súper destrozada, pues me dices, ¿vale? O sea, sin problema, eso. Sí, claro, sí, los medios.
Okay, I think we can start now. Good morning, everyone. I hope you enjoyed our social activity yesterday. but it's time to get back to physics, to reality. So today's session is about quantum computing, and as always, it's a pleasure to have our invited speaker, Ricardo Puebla. Ricardo is a Ramón y Cajal fellow researcher at Universidad Carlos III de Madrid, and he's an expert in many fields of quantum physics, such as quantum many-body systems, quantum control, quantum networks, or quantum sensing. So I don't want to be boring, and the floor is yours.
Okay. So, yeah. Thank you very much. Yeah. So thank you, Mitchell, for the introduction, and also thank you to the organizers. Well, I hope you hear me all right. Yes? Okay. So thank you to the organizer for arranging this event. I think it is really, really important that you continue doing this, so thank you for that. So basically, my name is Ricardo Puebla. I come from the University Carlos III, right? Despite that today's topic is quantum computing, I'm going to talk about quantum sensing, so completely different, right? But I hope I will motivate, or I will convince you that quantum sensing is really important, it's really useful, and is one of the main applications nowadays of quantum technologies, right? Okay, so let me start basically by introducing myself, and what I mean by that is basically to summarize the nomad research life, right, along these years. So I did the undergraduate and also the master's in the Universidad Complutense de Madrid, not far from here, right? And then I did the first jump. I went to Germany, to Ulm, where I did the PhD, right? Then, well, basically in the group of Martin Plenio. I don't know if it sounds familiar. And then after I did the second jump, I did the first postdoc in Belfast, in Northern Ireland, UK, right, in the group of Mauro Paternostro at that time. And then the pandemic came, right? I moved back to Spain, so I closed this triangle, and I moved to the CSIC, essentially to the building in front in the group of Juanjo García Ripoll. And then soon after, basically 1 year and a half after, I got a position in Carlos III as a visiting researcher, visiting professor. And then I got the Ramón y Cajal, where is basically where I am right now, right? Okay, so during these years, as Mitchell was saying, basically I have worked in many different topics. The main one, or let's say the first one, is where I did the PhD, which is essentially about quantum critical phenomena, understanding phase transition happening in quantum systems, right? Not only many body, not only many body, but also finite component systems that it sounds counterintuitive, but you can find also critical phenomena happening there. And then I also work on quantum control. Well, this is a bit. And quantum control, also quantum information processing. Quantum control meaning that you engineer sort of pulses or sequences in order to force your system to do what you want, right? Either to control the dynamics or to generate an effective interaction that leads to a desired gate, quantum gate, or to engineer a quantum state, right? You probably are familiar with these concepts. I also work on open quantum systems. Then recently, when I moved to the group of Juanjo here in the CSIC, I started with quantum networks. As you can see here, some illustration here, right? So basically, you have different quantum nodes that are linked by well, they are connected by quantum links, and that allow for the information exchange, right? And then also on quantum sensing and metrology, which is basically today's talk, right? Okay. So I divided the talk in different parts. So the first one is about a pedestrian introduction to quantum sensing and quantum metrology. It's just a general overview, try to motivate and what are the numbers that you can expect from such a systems, right? Why are they important? And then I will focus on nitrogen vacancy centers in Diamond, which are basically the leading platform, the leading hardware for quantum sensing. And then I will discuss some standard applications. So let's say standard meaning that the ones that we already know that they work, right, with MVs. And if I have time, I will talk about the specific contributions that I have in this field. So for me, basically my idea will be to cover these 3 points. And if I have time, probably not, right, then go into the details of these three. But essentially, I would be happy if by the end of the talk, I convince you about the difference between sensing and metrology. What is the working principle behind this, and also to give you an understanding or an overview of what is the hardware of these systems, right? And the protocols that you can do, right? Okay, and of course you can interrupt me at any time with questions. I mean, this is completely fine. Okay. Okay. So let me start with introduction, basically with sensing and metrology from a classical perspective, right? So sensors, we can define then sensors as devices that detect or measure a physical property and record, indicate, or otherwise respond to it, right? This is a dictionary definition, and well, I think it is really, I mean, it's intuitive, right? So we know sensors, and this is classical, and there are many examples. For example, in this case, basically a thermometer, right? That nowadays is so popular, right? And also you can have more complicated sensors that, for example, here I put in a mobile phone, because in your mobile phone you have essentially many sensors integrated, right? Like a compass, GPS, a camera, a microphone, everything is integrated there, and well, I don't have to convince you that this is really important, right? They are all over the place. Okay, so then what are quantum sensors? Okay, so quantum sensors, we are already throwing some quantum in it. So we could define it in the following way. Basically, there are devices that allow for the detection of a physical property or a signal using quantum effects. One could argue that essentially, since everything is quantum, even classical sensors are quantum sensors, right? But this is not what I mean here. What I mean here is that you use quantum effects in a meaningful way in order to detect the signal, right? And the expectation here, or the intuition, why these quantum sensors are important, is that since they are exploiting these quantum effects, they will be sensitive to quantum fluctuations, and therefore the sensitivity is going to be really large, right? Or well, basically that will allow you to get a very small precision, right? With these devices. Okay, so there are many examples, not as common, of course, as in the classical case. So one of them is the superconducting quantum interference devices, right? I don't know if you are familiar with them. They are called SQUIDs for short. And basically, is a superconducting circuit where you have you create like a loop, right, with two Josephson junctions in parallel, right? For those of you who don't know what a Josephson junction is essentially basically combination of a superconductor insulator superconductor, right, where you have a really thin insulator in between that allows for the tunneling of Cooper pairs, right? Okay, so this is here. This is a picture of what the circuit will look like, right? This is in a micrometer scale. And the idea here is that since we are working in the superconducting regime, right, the magnetic flux across the circuit, right, that is enclosed in this loop, it must be quantized. So it must be an integer of the magnetic flux quanta, which has this number. This is a constant. This is a constant, right? And therefore, since the magnetic flux is quantized, what it means is that if you input a magnetic flux externally, your circuit will create a superconducting current that will compensate that flux in such a way that you have an integer number right in between. And by doing that, basically, what you have is that depending on the magnetic field that is, or the flux that is across, you will see some oscillations in the voltage across the circuit, right? And these oscillations basically are sensitive to these magnetic flux quanta. And therefore, basically, what you have is a really sensitive device to detect magnetic fields. Of course, this is in terms of the magnetic flux, right? So the larger your squid, the more sensitive you will be for the magnetic field, right? But by doing that, basically, you sacrifice the spatial resolution, right? So what you want to do is to create or to be in between, basically, where you have still a good spatial resolution and a good sensitivity for the magnetic field. And just to put you some numbers, if you scan in the literature, this is the sensitivity that you can find with these devices, right? It's in the order of femtoteslas divided by the square root of hertz. And if you panic as me when I see these sort of units, right, where you have this square root of hertz, basically what it's telling you, this is just a way in which you can quantify the sensitivity without referring to the integration time over which you are averaging the signal, right? So in order to get the accuracy, what you have to multiply is this number times the square root of 1 over t, where t is the time in which you are collecting data, essentially, right? So for instance, here if I perform the experiment in 1 second, right, what I will have is an accuracy in femtoteslas. And I don't know if you know something about or a signal that is with, let's say, at the femtoteslas magnitude. But to put you a context with the numbers, you know that basically the magnetic field of the Earth is in the range of microteslas, right? Essentially here, I think in Madrid is 45, around 45 microteslas. So with these devices, basically we are 9 order of magnitudes below that. So it is incredibly sensitive, right? We have an accuracy that is amazing. And so therefore we can think already pushing this down, right? And so for example, if we compute, or basically you estimate the magnetic field that neurons will create, right? Because basically neurons are firing some electrical current, right? So they will generate some magnetic field. And well, depending on the distance, of course, you will have a range of values, but they range from tens of or hundreds of femtoteslas to tens of picoteslas, right? So essentially, these devices will allow you to detect the magnetic field that your brain is producing, right? Which is simply amazing. And of course, people thought about this and they created a machine, right? So basically, you can put your head inside this helmet where you have an array of squids that are in the superconducting regime. So basically, inside you have liquid helium, I think, in order to be operating in the superconducting regime, right? Of course, you don't feel the liquid helium in your head, otherwise it would be a problem, right? But this way, basically, you can perform a map of the magnetic activity of your brain, which is amazing, right? Okay, another example, I think it is well, quite popular, right? Is the laser interferometry in LIGO, no? In the Laser Interferometer Gravitational Wave Observatory, right? Where they do this, well, they have a quantum sensor in a way, basically, by, well, this is nothing but a Michelson interferometer, right? Where they inject a laser, then you have a beam splitter, it goes through branches, to arms, right? And then interfere at the photodiode in such a way that essentially if nothing happens, if the length are completely, if there is no perturbation, right, then essentially you don't detect any photon. It is quantum interference, right, destructive interference. Well, this device is essentially one of the most sensitive devices that we have ever built, right? So here it is, the sensitivity is 10 to the minus 22 without units, because this is basically comparing the relative distance between the two arms, right? And this is, I think, is around 4 kilometers long. Okay, so basically what we know is that the gravitational waves, or at least those that have been detected, will stretch or compress one of the arms by 10 to the minus 18 meters. And this is something that you can detect thanks to this interferometer, right? Which is, again, amazing. It's astonishing. And just to go, again, to give you a sense of how small this number is, right? Consider, for instance, a proton, right? A proton is essentially 1.6 10 to the minus 15 meters in the diameter, right? So essentially, the gravitational waves that we are detecting is 1,000 times smaller than the length of a proton. So this is, again, really mind-blowing, right? Okay. And another example of a quantum sensor that is perhaps more mundane, right, is more pedestrian, if you want, is nuclear magnetic resonance and magnetic resonance imaging, that despite it is really common, it is, again, really interesting and really, really interesting, right? Because basically what you do here is you apply a large magnetic field along one axis, right? For instance here, perpendicular, in such a way that essentially the nuclear spins, they will try to polarize in this direction, right? Then you apply a pulse in that you put the spin in the XY plane, and this will start to precess and will start rotating at the Larmor frequency. This generates a signal that is the one that you record. And by recording this signal, then you can do images and you can detect the concentration of certain nuclei and so on. Right? So again, this is really, really impressive. I will come back to that because it shares many similarities with MV centers. Okay. So then, what is quantum sensing? Well, I could define quantum sensing essentially as follows. It's basically the study of quantum effects for detection of physical properties, right? So what about quantum metrology? What do you think is quantum metrology? Well, essentially quantum metrology is the same thing, right? So we are referring about essentially the same thing. Quantum metrology refers to the study of quantum effects for detection of physical properties. So you could argue that essentially the two fields are the same because they are studying the same thing. And this is something that you can actually find, for instance, in the pillars of quantum technologies. This is taken from the European Quantum Flagship, right? We have the 4 pillars. We know communication, right? Computation, simulation, and then you will have sensing and metrology. That despite they are the same, they are put explicitly with different names, right? Sensing and metrology, it is the same pillar, but we have both names, right? So if you ask me, are they the same? Well, they are studying the same thing, right? But from different points of view. Basically, quantum sensing is more practical, quantum metrology is more mathematical, it's more formal. And this is what I'm trying to motivate here. So quantum metrology is basically comes from more information theory, right? So you try to quantify in a formal way what is the advantage that you can get with quantum effects, right? For the parameter estimation. And you are interested, typically in quantum metrology, you are interested in knowing the fundamental limit for your precision. So how precise can I be provided by the rules of quantum mechanics? This is basically the question in quantum metrology. So what about quantum sensing? Well, quantum sensing is more practical, is more focused on an application, right? So it's more oriented in a particular setup. What can I do with this setup, right? And it's not so much focused on fundamental limits in the sense that if I want to detect gravitational waves and I have a device that is already sensitive enough for that, who cares if I'm in the fundamental limit of quantum mechanics, right? It basically works, right? And I could say the same if I have a classical device. If I want to measure the temperature here in Madrid, I don't need a quantum thermometer for that, right? Because I already have the precision, right? So quantum sensing is more in this engineering, if you want, or application point of view. Still, they are referring to the same thing. So it's using quantum resources for the detection of physical properties. Okay. And now what follows is a bit trying to formalize what quantum metrology is, because I'm not going to enter more in details. As I told you at the beginning, basically I want to discuss the applications with a particular hardware, right, with MVs. But in order to put a distance with quantum metrology, I thought it would be a good idea to introduce basically what is the interest in, or what is the focus of quantum metrology. So this is what I'm going to do next. And well, basically, since it is more formal and more mathematical, we'll have equations. So apologies for that in advance. I hope I will not bore you with many equations. So basically, it goes as follows, right? So let me start with classical metrology, right? And in classical metrology, basically, it's a classical system, right? You have X, that is a random variable that is drawn from a probability distribution. And this random variable is nothing but the measurement that you are recording from your device. So it could be the distance that you are, I don't know, with your scale. It could be the temperature of your thermometer. It could be anything classical, right? And here, what you want to do is to estimate this parameter theta that is the target. Again, it could be temperature, it could be the distance, it could be the thing that you are interested in, right? And depending on the value of theta, right, so you might have two different values, so theta 1 and theta 2. These probability distributions conditioned to that value will be different, right? So whenever I measure the temperature here in Madrid or in the North Pole, I will have different values. So, different values that they will follow or will be drawn from a different probability distribution, right? Okay, so then in metrology, what you do is you define a unbiased estimator. Basically what it means is that you take the outcomes, the measurements, X, and then you do something with them, and you in such a way that the expectation value of that will give you the target parameter that you want to estimate. It could be the mean, right? It could be the mean of the measurements, or it could be a complicated function. The point is that if I perform sufficiently measurements, I expect to get the target parameter, right? This is basically the idea. Okay, this is fine, but this is really unsatisfactory, right? Because even though I know that I will converge to the mean, I want to know how precise I will be, right? So this is essentially the point of quantum metrology. I want to quantify, or at least put some bounds on the precision that I can achieve. And the answer to that comes from Fisher information and also the Kramer-Rao bound. Yeah, so in order to do that, have some equations. So you have to define a useful quantity, right, which is this G, which is nothing but the partial derivative of the log probability and distribution respect to the parameter that you want to estimate. This is basically, now it's just ad hoc. I introduce this quantity, right, because it will prove to be really useful. And it will be useful to bound essentially the precision, the variance of the estimator, essentially, okay? Okay, so the first step in order to get this Kramer-Rao bound, or what is the precision, the best I can hope for, is to show that the expectation value of this new defined quantity is equal to 0, right? And then you have to play around with the definitions, right? Basically, it will be the integral over the space respect to this quantity G, right? So you take the partial derivative of this log probability, right? So you get this part here, so you cancel out this probability with that one there, right? And basically you end up with this quantity here, this integral, and then you assume that the probability distribution is regular, right? Basically, as in physics, we do many times, we interchange the integral with the derivative, we close our eyes, it works, right, fine. And then essentially, what is this? So basically, it's the integral of a probability distribution, so this must be 1 because it's normalized, right? So then you end up basically with a derivative of a number of 1, so this is 0, fine. So we prove it. This is the first step. Then the second step is to use the Cauchy-Schwarz inequality. So you have the variance of your estimator times the variance of this quantity, and this must be larger or equal than the covariance between them. This is basically a reformulation of the Cauchy-Schwarz, fine. And here the covariance is basically the expectation value of covariance between A and B is basically the expectation value of A minus the mean of A times B minus the mean of B, right? And if it happens that the expectation value of one of those quantities is equal to 0, then you simplify a lot this expression. So the covariance of A and B is essentially the expectation value of A times B. And this is essentially what we have, right? Because the expectation value of G is equal to 0, as we just seen. Okay, so, yeah. Then essentially the third step is to show, well, we have showed that the covariance of G and the estimator is equal to the expectation value of those, right? So the third step is to show that this is equal to 1. And again, this is very similar. You play around with the definitions, right? So I will be quick, sorry for the equations. Basically, it's the same as before, but now, so before we had the expectation value of G without the estimator. Now we have the estimator here, right? So it appears there. So you do the same tricks. You do the partial derivative of the logarithm, right? You cancel out this probability here. But now, essentially, what you end up is with this quantity, right? So you have the integral over the estimator times the partial derivative of the probability. Again, we close our eyes, we put the partial derivative in front of the integral, right? And then we have that, right? So this is basically the expectation value of the estimator. So by definition, if we are choosing an unbiased estimator, this is theta, right? This is the parameter that we want to estimate. Then you take the partial derivative, well, you get 1. Fine. Why I'm saying this? Because now, if I'm combining everything together, right, what I had was that the variance of the estimator times the variance of G is larger than or equal than the covariance. It turns out that the covariance is equal to 1, so I can express the variance of the estimator as an inequality, no, this must be larger or equal than 1 over the variance of G. And this is precisely the Fisher information, right? So that variance of this quantity that I introduced, it turns out that it is the Fisher information. And it's basically telling you how precise can I expect my estimator of the parameter to be, given that I have a probability distribution from which I'm sampling the outcomes, right? And of course, what you want to do is that the larger the Fisher information, the more precise you can be, right? This is the play always. This is the game in metrology or quantum metrology. Fisher information, larger Fisher information means better, right? Okay, so then basically you can play again around with the definitions. So Fisher information is the expectation value of that. It was the variance, but given that the expectation value of G is equal to 0, well, you can express it like that. Equivalent definition, you can write it like this. This again playing around with the logarithms and the partial derivative. It's not really important. Okay, so just an example. Remember, this is classical, right? So imagine that we have a probability distribution of the outcomes that follow a Gaussian distribution, right? This is quite a standard, right? In many situations, right? So if I have this probability distribution, then what I need to calculate is the Fisher information in order to put a bound to the precision, right? And the Fisher information, in order to compute the Fisher information, I need this G, which is a partial derivative of the log of the probability, right? So if you do the calculation, basically you get this expression, and then you calculate the expectation value of that, or with this definition, basically at the end of the day, the Fisher information is n times, n being the number of measurements, divided by the variance of how basically far apart are with respect to the mean, right? Good, so now if we put that into the Kramer-Rao bound, basically we can bound the variance or the standard deviation of my estimator, right, in this way. Basically, it will be larger than the sigma divided by the square root of n. And this is a way, basically, to state what we already knew, right? This is the central limit theorem, in a way, right? And this is a fundamental classical limit, right? So with classical physics, in a way, basically, you are limited by this scaling factor. So in order to improve your estimator, what you have to do is to increase the number of measurements, and you will reduce the uncertainty by 1 over the square root of n, right? So this is standard. And what about quantum metrology? Well, in quantum metrology, or in quantum setting, we don't have a single probability distribution, right? We have many because we can measure different observables, right? But for each different observable, I will have a classical probability distribution, right? So in a way, if I choose an observable B with outcomes smaller b, right? We already know this. And then I will define a Fisher information for this particular observable. Fine. And then what you do in quantum mechanics or in quantum metrology is that you define the quantum information as the maximum over the observables that you can measure, right? So quantum information in this way, basically, it will be always larger or equal than the classical Fisher information because you are maximizing over all possible measurements that you can do in your system. Okay, so in this way, this is the this is definition. If you do the math, you can also express this in this more complicated formula, which is essentially a second derivative with respect to a tiny variation of your parameter and in terms of the quantum fidelity between your state and the state that is perturbed. Fine, this is more technical, but just let me just say that from here to there, you can show this, okay? So it's in terms of the quantum fidelity. How distinguishable are the states when you perturb them, right? This is the main idea. Okay, so this is then the quantum Kramer Rao bound. You can do it essentially in the same way as we did before. You put the bound into the standard deviation of your estimated parameter, which will be essentially 1 over the square root of the quantum fission information. Fine. Okay, so let me consider a simple case, just for the illustration of this. Imagine that we are considering pure states, and you have unitary time evolution, or unitary evolution, right? So what I mean here is that you prepare your system in a state, and then you evolve it with this unitary. That depends on the parameter you want to estimate, right? This is the idea, basically. I prepare, I let it evolve, and I want to estimate, essentially, this phase, theta, here, right? Fine. Okay, so in this way, if you do that, one can show that the quantum fission information has a particular simple expression, which is nothing but the variance of the energy with respect to this H, this operator that could be associated to a Hamiltonian, if you want, because this will be basically like a Hamiltonian evolution, right? Fine. So this will be the quantum fission information. So let me go a bit beyond that. So let's consider qubits, right? So in particular, a single qubit, right? So I have a single qubit. This is like in a quantum circuit diagram. I prepare the state, I let it evolve, and then I measure. And the question is how accurate I can determine this theta, right, in this unitary evolution. So just for the sake of the example, let me just take that the unitary evolution is just a sigma c, right? And I'm preparing the state in a plus state, right? Fine. Then basically, in order to know how much information can I extract from this system, I have to compute the quantum fission information, which is the variance of this energy, where the energy is basically a sigma c. So basically here I have the expectation value of sigma c in a plus state. So this is 0, right, essentially. And then I have the expectation value of h squared. H squared basically is the square of sigma c, and the square of sigma c is just 1, right? So basically I end up with a quantum fission information that is 4. Why? Whatever it means, right, is 4. So this puts a bound in the precision that I can get, but here I'm just considering a single shot, a single measurement, right? What happens if I repeat this n times? Well, if you repeat this n times and you consider essentially independent qubits, which is essentially as the same as saying that I'm repeating the experiment n times, right? They are independent. Well, essentially, since they are independent, the quantum fission information adapts, right? So you will have, instead of 4, you will have 4n, right? Because you have n qubits that are independent. And then you end up with this precision bound, this 1 over the square root of n. And again, here the important thing is this scaling, right? So we are recovering the square root of n dependence, as in the classical case, right? So this is known as the fundamental classical limit, or also very confusingly known as the standard quantum limit, right? So then the question of quantum metrology is, can we do better? Can we do better with these systems? Basically, what I'm considering here is that I have independent qubits, right? But we know that we could entangle them, right? So I could essentially try to see whether quantum correlations will enhance the precision, right? This is the idea. And again, just for the illustration, let me consider that instead of having independent qubits, now I have a non-local state, the GH set state, basically balanced superposition of all spins up, all spins down, right? And in this way, basically, then each of these qubits will undergo this unitary evolution that is still local, right? There is no cross correlations there. Okay, so if you do the math, then in order to estimate what is the quantum fission information in this case, you have to compute this quantity, right? But now where this state is the entangled state, right? The GH set. Well, this is particularly simple, right? Because I have to compute this expectation value of H, where it is the sum of the sigma c's, right? And remember that basically in the GH set is all spins up plus all spins down. If I multiply by a sigma c, what I do is essentially to flip the sign, right? It doesn't really matter which spin or which qubit. Basically, I will get a minus sign. And therefore, basically, what I'm doing is to to create a state that is orthogonal to the initial one, right? So in this way, basically the expectation value, it will be 0, right? Fine. What about the other part, the expectation value of h squared? Well, here's where the magic happens, right? Because in this case, you have the expectation value of this quantity here, so the sum over I and j from 1 to n, and the product of the sigmas, sigma c's, right, the Pauli matrices. And here is this is where the magic happens, because essentially here you are flipping the spins twice, right? So flipping the spins twice means that basically you go to the -1 and then again to the -1, so you recover the initial state, and therefore all the terms in this sum contribute with a 1, so you add them together and you have an n squared contribution. Fine, so now we go to the quantum efficiency information and we find that it basically scales with n squared, right? You put the Kramer-Rao bound, and magically, basically what we have is that the precision now scales, instead of the square root of n, with n. So we have an n-fold improvement over the classical setting, right? And this is known as the Heisenberg limit. And this is why people got so excited about quantum metrology, because essentially it's telling you that entanglement, in this particular case entanglement, quantum correlations in general can help to boost the precision in parameter estimation. So by using quantum correlations, I can do better than classical, right? And this is essentially the main focus of quantum metrology. They are interested in knowing these fundamental limits. So to push the systems to scale better than classical, in a way, okay? Okay, this is for qubits. With this, I will finish the boring part of the equation. Sorry for that. But you can do also for bosonic oscillators, basically for single mode light, for example, right? Essentially, in this case, basically you have a bosonic system, right? A single mode, and again, the unitary evolution instead of the sigma c is nothing but a rotation in the phase space. Fine, right? So then you will think, what is the best state here in order to boost the precision for your parameter estimation, right? So let me just consider two particular cases, the coherent states. So if you do the math, basically what you will find is that the efficient information scales with the average number of photons. Of course, here we don't have the notion of a number of particles because, well, we are dealing with bosons, right? So, but still we can express the efficient information in terms of the average occupation number, right? So this also tells you the energy of your system, right? So the more photons, the more energy you have, and the idea here is that the more energy you put in your system, the more precise you will be, you expect to be, right? So again, if drawing the analogy with the case of in the case of qubits, basically this will be like the standard quantum limit, right? Because the quantum efficient information is scaling linearly with n, right? So whenever you do the Kramer-Rao bound, you have this dependence with the square root of n. Fine. So can we do it? And can we do better than this? Yes. So for example, if you consider squeeze states, that you know basically is when you squeeze in one of the directions in the phase space and you stretch the other one, right? If you do the math, well, you find this formula for the efficient information. And basically you have two contributions, one that is linear with n, another one that is quadratic. So for low occupation numbers, basically you will have a linear dependence because this one will be much smaller than n, right? For n being smaller than 1, much smaller than 1. But whenever you put more energy into the system, you have more photons, right? Then this quadratic term starts to dominate, and therefore we are pushing the system, the precision, towards the Heisenberg limit, right? So that's why a squeeze state or a squeeze state of light are so interesting, right? And just to draw the analogy with what I told you before, in LIGO, I think they are already using a squeeze light to boost the precision, right? So this is one of the reasons. Okay. So with that, I close this first part. I hope I convinced you the difference between quantum metrology and quantum sensing, and I will go now deeper in quantum sensing, in particular in the MV centers. So the main take-home message here is that quantum resources can enhance parameter estimation, so particularly for the Heisenberg limit, right? And On the other hand, quantum sensing is more focused on a practical approach, and it might be that your system, right, in a quantum sensor, is still operating in the standard quantum limit, but it doesn't mean that it's not interesting, right? Still, the sensitivity can be really large. Okay, so not sure if you have questions so far about this part, or any question, any comment? No? Okay, so then I continue. Fine. So, okay. So let me continue with MB centers, right? So now I'm shifting focus. Now there are not going to be so many equations as before. It is more like a qualitative or introduction to MB centers in diamond. Okay, so here you have a shiny, beautiful diamond, right? And that we know is the hardest material that we know. And this is because the lattice structure, so the atomic structure of diamond, right, is made of carbons, right? And they are really densely packed, and they form this covalent bond between them. And well, this is the unit cell of the diamond, right? And here you have the carbon atoms, right? So the length of this unit cell is about 0.3 nanometers, and well, that's why it's one of the hardest materials. It's the hardest material, right? Okay, so what we know is that you can have a diamond, right, with this beautiful lattice structure, but there can be defects, right? You can have defects in the lattice, and one of the, well, for example, you can have translocations, right? So where you don't match exactly the continuation of the lattice over in space, you will have like a translocation. Or you can also have defects where instead of having a carbon in the lattice, you have a different atom, right? So, and there are many examples of defects that can happen, and they are essentially really common in diamond or any other material, right? For example, here, one of the common defects that you can find in diamond is that instead of having a carbon, you have a silicon atom, and when you place, or essentially you replace this carbon by a silicon, basically you expel two adjacent carbons in the lattice, and you create basically an empty space, and this is known as a vacancy, right? So in this way, basically this defect is known as a silicon vacancy, and you have two vacancies in the nearby positions of the silicon. Another interesting defect is MB, where basically you replace one of the carbons by one nitrogen, right? And by doing that, you expel, you basically create an empty space where it should be a carbon. Now you have a vacancy, right? So MB center basically stands for nitrogen vacancy centers, right? And this is a defect that can happen in the diamond lattice of your material, of the diamond, right? Okay, so there are many different defects that can happen, right? And these defects, depending on the nature of these defects, is essentially the ones that they give you color to the diamond, that otherwise is transparent, right? So you can have bluish diamonds, more yellow, pink, are not sure what color this will, probably it's more transparent, you know. Okay, so yeah, this is something that you can do artificially by implantation, and you can create these colors of these beautiful diamonds that you can buy, actually, if you want. Okay, so you can go even more, and you can create defects that fluoresce. So basically, you can create a diamond that glows when subject to a particular light, like a UV light, right? That otherwise seems like normal diamond to when subject to normal light. If you put this UV light, you will have a glowing diamond. It's really, really cool, right? So you can create these sort of materials. Okay, so for us, we are going to be focusing on MB centers, right? So if you have a high concentration of these defects in the diamond lattice, what you will create is a pinkish diamond, right? That will look like that. No? This is also nice. But of course, whenever you do experiments, you don't have such a piece of diamond, right? You have something more like this, right? It might be a bit disappointing, but it is essentially the slab of the sample that you use for the experiments, right? It's just a diamond there, and you can see essentially a bit like reddish color. Okay, and as I told you, basically the MB center is replacing one carbon and then spelling another carbon in the lattice, so you create this vacancy, but this vacancy can be in one of the 4 positions that are close to the nitrogen, right? So this means essentially that the MB will have 4 different orientations in the lattice. And there is nothing you can do about that, in the sense that whenever you have defects, they will happen in these 4 orientations randomly, right? You can favor, by implantation and fabrication, you can favor one of these orientations, but you don't cancel directly the others, right? So this is sometimes a limitation, sometimes it is useful, depending on what you want to do. Okay. Fine, so basically, why MB centers are so popular nowadays for quantum sensing or other applications as well? Well, basically because they combine a very nice properties. So the first one is that it's easy to manufacture, to produce, right? So you can produce diamonds in 2D layers. You can create a tailored implantation, in one place. You can create these MBs as nanoparticles, right? Because you can basically create the diamonds in tiny particles, right? Where you will have MBs. So you can do many sort of things with this material. It is also a stable defect in the sense that once you have created, then it will stay there. There is nothing you have to worry about. It will stay there always, right? Well, always, depending on the conditions, right? But in a way, it's really stable for years even. And well, it is biocompatible, right? We are dealing with diamond. It's made of carbons, so this is completely biocompatible. So this makes it really interesting for bio applications and medicine, right? It also has a qubit-like degree of freedom, and I will come back to that in a second. So basically, this defect, or in this defect, you can encode a qubit, right? And essentially, it's like a spin 1 electron that you have in your diamond. And this qubit degree of freedom has good coherence properties, even at room temperature. And this is the killing point, right? So you can do experiments, quantum experiments, even at room temperature, normal conditions. You don't need sophisticated techniques to cool down your system, as in compared to other systems like trap ions or superconducting circuits, right? And this makes it really popular, right? Because and cheap. Also, you can do in order to prepare this qubit state is done by optical lasers. Basically, you shine lasers in order to prepare and read out the information, right? And on the other hand, essentially, in order to control the qubit states, you apply microwaves. So in a way, basically, we know, no, not me, because I'm not an experimentalist, but we know how to manipulate basically lasers, fine. And we know we have also a really strong, let's say, know-how in microwave fields, microwave control. So basically, you have many good properties, and that's why it's so popular for quantum sensing. And as I briefly mentioned before, right, the fact that it works at room temperature makes it even more interesting. And for that, let me just show this. So probably you recognize already what is here, right? This is the IBM quantum computer, fine, based with using quantum circuits, superconducting quantum circuits, right? And here on the left, I put a picture of the laboratory of David Lucas at Oxford University. This is basically a trap ion lab. As you can see, it looks like a mess, but I promise you that every single beam splitter or laser that is there is properly calibrated in order that this experiment works. So it's simply amazing. So I'm going to throw you a question. So how much money do you think it costs to create or to have this quantum computer or this lab? What do you think? What is the cost associated to this? Can you guess, roughly? Millions? Tens of millions? Or 1 million? Yeah, exactly. So basically it's around tens of millions, so typically we'll say 30, 50 millions, right? To produce a quantum computer or a lab. Of course, this can depend a lot on the specific devices that you have there, right? But this is more or less the cost associated to that. Now, compare this to an MB lab. This is essentially what we have at the University Carlos III, right? So as you can see, well, I mean, there is electronics involved, right? But the fact that I can do a picture really close to it really tells you that this is simple, right? And the first point, the first killing point, as I mentioned before, is that this operates at room temperature. So you don't care about the cooling down the system. And this removes a lot of cost, right? And also the pressure, right? In trap ions, you need a high vacuum chamber in order to do the experiments. Here, no, right? I mean, this is operating just here, like in normal conditions. And the cost associated to these sort of labs is around 100,000 euros, more or less. So we are orders of magnitude smaller, no, cheaper than superconducting circuits or trap ions. So that's why if you want to do just experiments with quantum experiments at room temperature, this is the way to go, of course. And if you want to do experiments or quantum sensing of in biology or in medicine, there is no way you basically can. I mean, there is no way you can use trap ions for that, right? Because you will be freezing your cells or whatever, right? It's no longer alive in that regimes. So this is the way to go, right? And of course, this is I show you the pictures that we had at Carlos III, but you can also buy this, and there are companies selling these devices. And as you can see, this is not bigger than a desktop computer, right? So you have there, everything is integrated. You have the lasers, you have the microwaves, and you have a sample. And I think in this particular case, they are using MBs for scanning, right? I will mention later on what I mean by that. But it's something that you can buy, and it's not, I mean, it's like a desktop computer, right? Fine. Okay, so let's go a bit deeper in the details of the hardware, right? What a MB looks like. As I told you, basically, we are replacing a carbon with a nitrogen. Then we have a vacancy. So we have a direction of the spin axis, right? This defect basically have a level structure, right? So have some energy levels that, well, you can compute them, right? And they will sit within the bandgap of the semiconductor, of the diamond semiconductor bandgap, right? And so basically you have two main manifolds. So you have this 3A2, doesn't really matter the nomenclature, right? So basically there are three states that we have here. There's the low energy states, and then we have an excited manifold, right? And we have three projections of the spin. Basically, remember that this is a spin 1, so basically we have three different projections. So NMS can be either 0, +1, or -1, depending on the projection of the spin, right? And in between, we have also some intermediate states that basically will help for the helping the decay path of the process. Basically, if you put energy into the system to go up, this will decay. They will decay either in this transition or through the intermediate states. Fine. So this is what I'm trying to motivate here, right? So in order to do something quantum with these devices, well, you first need to prepare the state in a quantum state, right? So I told you that this works at room temperature. So if you do the math, basically what you have is an equal population of these three states. Basically, you have a classical state, right? So in order to do something quantum, you need to prepare in a quantum state, so like a pure state. And in order to do that, basically, what you do is to shine a green laser to the states, and this basically will take the energy. They will go to the highest the excited state manifold, and they will decay. And they will decay depending on the different paths in the structure, right? So basically, let me just focus on the first one. So if you are in the 0 state and you shine the green laser, you go up, and this optical transition conserves the spin, right? So basically, you go to the 0, and then this 0 state has a very low probability to go to the intermediate states. So mainly decays down again by emitting a red photon, essentially, right? So you will see red photons coming out of your MB, of your diamond. That's why it's pinkish, it's a reddish color, right? Okay, so if you do the same for the plus and minus states, -1 states, right? You go up, and then you can go still down by emitting the same red photon, but you have a larger probability to go to the other path through these intermediate states that then they decay, they don't emit photons, well, in the infrared, but it doesn't really matter, right? And then you populate equally, once you go this line, you populate equally to the plus, minus, and the 0. So basically, by repeating this process in a continuous fashion, right? Basically, you are shining with your green laser. What you end up is by accumulating population in the 0 state. Because once you have population in the 0 state, it's confined to go up and down. It doesn't go through this transition. So you are accumulating population here. So at the end of the day, basically, if you repeat this during microseconds or in milliseconds even, you can get a good fidelity for your state preparation. Basically, you prepare your MB in the 0 state, right? And just let me explain that. I think I forgot. Basically, these plus and minus states are separated from the 0 energetically by this D, which is in the order of gigahertz, right? 2.8 gigahertz, and this is known as the 0 field splitting. And it comes essentially. This is due to the fact that we have electrons in the defect that are coupled, so you have this sort of splitting at 0 field. If you apply a magnetic field, then the 0 state doesn't really change, right? The projection is 0. The plus and minus states, they will split according to the Zeeman splitting, right? So basically, they will split by 2 times the gyromagnetic ratio times the magnetic field along the axis of your MB. I hope this is understandable, right? So in this way, basically by shining the green laser, you prepare your state, and in order to read, you do the same. Because what we see here is that if you have population in the 0 state and you apply the green laser, then it will go up and then down. So basically, the 0 state will emit photons, red photons, right? And however, if you are in the plus and minus states, you will go up, and then mainly you will decay through this non-radiative process. So at the beginning, you will see that more photons if your state was in 0, right? And this is the way in which you can read out the qubit, or let's say the internal degrees of freedom of the MB, basically by looking at the intensity of the red photons that you are detecting with a photodetector. So the behavior is typically like that. So if you are in the 0 state, it is brighter. So you apply the lasers, you collect more photons, and then basically, because this process is the same one that we are using to prepare the state in the 0, right? At a certain point, you accumulate the population again in the 0 state. So both behaviors, right, they merge, and you cannot really distinguish what was your initial state. Fine. But this is just a way in which you can read out and you perform measurements in this system, right? Okay. So the Hamiltonian, no, for the Hamiltonian lovers, basically this is the Hamiltonian of the MB. It's really simple, right? So it's a spin 1. So you have the 0 field splitting, this D, that it was basically the 2.8 gigahertz. And then depending on the magnetic field that you apply, then you split these plus and minus states in terms of the gyromagnetic ratio of the electron, right? So basically for milliteslas, you will split this by 56 megahertz, right? The difference in energy between the plus and minus 1 state. And since we are dealing with a spin 1, basically we don't have the Pauli matrices, but the ones for the spin 1, right? That look like that. Fine. Okay. Good. So on the typical sketch of this setup is the following, right? So you have the green laser that you need in order to prepare and also read. And you can have microwave in order to control these internal degrees of freedom, the internal states. And then whenever you apply the laser, the green laser, you will see scattered photons going out, the ones that you detect. So basically, everything can be understood in terms of these 3 components, right? This is everything you need. And for the Hamiltonian, basically, this is the internal levels. And if you apply a microwave radiation, this is the one that are controlling the internal degrees of freedom. So typically, it looks like that, right? Fine. This is basically a standard in light matter interaction. Okay. So this is for the hardware, right? Then then we know that we can do many cool things in quantum sensing with MBs, right? And here this is a summary taken from this review paper that is really nice and really exhaustive. And just to give you an overview, basically, you can see, for instance, the thermal measurements with a nanodiamond. So you have a nanodiamond with an MB, and MBs allows you to detect basically the temperature of what you have nearby, right? So this is also really cool. So you can do also in vivo magnetic activity in animals, right? Like in a mouse, you can probe essentially what is the magnetic field, for instance, in the brain, something like that. You can also use MB for detecting molecular structure of a protein, for example, that is attached to the surface of the diamond, because you can couple the MB with some spin labels that you put in the proteins, because you have dipole-dipole coupling and so on. If I have time, I will explain that in more detail. And there are many other applications. So, what do we do with this? What are the protocols that are involved in quantum sensing? Well, the first one, and this is probably the simplest, is relaxometry. Relaxometry, it comes back, or basically falls back to the ideas of nuclear magnetic resonance. So if they were already there, actually we use them every day in hospitals to perform images, right? So let me sketch the idea here. So the point is that the coherence and relaxation of a quantum system, a qubit, can be beneficial, can be actually something that you can use in order to detect your environment. And this is essentially what you want in a quantum sensor, right? You want to detect what your environment is. So the key point here is that the coherence depends on the noise depends on where your qubit is sitting, right? So for example, in magnetic resonance imaging, what you do, again, you apply this large magnetic field in one direction, then you apply a pulse to put it in the XY plane. This will start rotating at the Larmor frequency, right? And then you record the magnetization of your sample, right? And then you will see some decaying behavior, something like that, right? So for example, the orange curve, right? So we'll see a decaying magnetization. This is essentially because of the coherence, right? The T2 time. And then this will depend, this behavior, the difference behavior between basically the T2 times, how fast this goes down, it depends on the environment. And by knowing essentially or associating a value to these signals in a gray color scheme, right? Basically you can create essentially an image of a brain, for example. This is essentially what you use in magnetic resonance imaging, is essentially to know how this magnetization decays. And you use it for images, right? So in MBs, we can do essentially the same, right? So we have the MB, we prepare it, and then we do nothing. Basically, we let it evolve, we let it interact with your environment. That, for example, will be like a concentration of molecules that are near to the surface and so on. And depending on the concentration and depending on the type of molecules or spins that you have there, you will expect more noise or less noise, right? More noise means basically more the coherence. Less noise means less the coherence, right? And therefore, you will have different behavior of decaying of your population of the qubit. By doing that, essentially, you can know what is the concentration of a particular electron or nuclei, right? And this is essentially super simple because you don't do anything, right? You prepare, let it evolve, and measure. And with that, you already have information about your system. And in this particular case, basically, there is no microwave field. Just do nothing. You prepare it, and then you prepare the state, and then you read it. And here will be, I think this has been done with the gadolinium because it creates magnetic noise that is quasi-resonant with MB. Fine. This is just an illustration. The other thing that is really important is optically detected magnetic resonance, right? The ODMR for short. And this is basically a demonstration that your MB is a magnetometer. It allows you to measure, to detect magnetic fields really easily. And the underlying idea here is that basically you have your internal levels of the MB, right? So let me consider first what happens whenever we have a zero field, no magnetic field, right? So basically the plus and minus states are degenerate, they have the same energy, right? And then you send microwave field. and the laser also in a continuous way. Basically, you are pumping continuously at the same time with the microwave. You are creating transitions. And then you sweep the frequency of your microwave field in such a way that basically, if you are far between of the energy difference between these states, you don't do anything to the MB, right? And basically, you are collecting photons, a large number of photons that are scattered because of the zero state. Fine. But whenever you match, essentially your frequency of the microwave matches this energy splitting of the MB, then you will be pumping population from the 0 to the plus and minus state, and therefore you are losing photons, right? Because the plus and minus states are less bright than the 0, right? So you will see a dip in the fluorescence that you are recording. And by doing that, scanning the frequency, you will see a dip basically at essentially the energy splitting between these two states that correspond to the zero field splitting. Fine. Now, what happens whenever I have a magnetic field that is different from 0? Well, they split, right? The plus and minus, they are no longer degenerate, and the energy difference between them is proportional to the magnetic field that you are applying, right? Or that you want to detect. And again, you can repeat essentially the same process. You send the microwave sweeping in the frequency, and then instead of seeing now one single dip, you will see two, right? And you will see two because you have two transitions right now. So one will correspond to driving the 0 and the plus 1 state. Basically, it will be the zero field splitting D plus the energy separation, right? So plus the general magnetic ratio times the magnetic field. And the other one corresponds to the minus transition, right? And this is an experiment. This is really nice because you only need to record the intensity of your red photons, right? And you will see these two dips. And by knowing the locational in frequency of these two dips, and you basically see the distance, you already know what is the magnetic field because it's simply proportional to that. So in this way, basically, you are probing, you know what is the magnetic field along the axis of the MB, right? This is a very simple experiment. Of course, if you do this, that will be for a single MB because you only have one orientation. But in reality, as I told you at the beginning, you have 4 different orientations at random in your diamond, right? So you will have 4 different projections of the magnetic field. So if you do this in an experiment with many MBs, what you will see is essentially 8 dips, right? And for example, here you will have 2, the second, right, the third, and the fourth. Each of them are measuring or are subject to a different projection of the magnetic field depending on the axis of the MB, right? By doing this, basically you can reconstruct the whole orientation of the magnetic field, right? Not only along one axis, but in the whole space, basically the 3 components of the magnetic field. So you have a vector magnetometer in your diamond. You can go on with that, and you can perform the ODMR, basically the same idea, without basically at zero field, right? Without magnetic field. And the main idea here is that you can use this dip of the zero field splitting to sense changes in the temperature, because we know essentially that the zero field splitting comes because the distance between the electrons are forming the spin 1 of the MB, right? So as you increase the temperature, the diamond will expand, right? And therefore, the zero field splitting will change, will be dependent on the temperature of your diamond. Therefore, and basically this is something that you can, it has been calibrated, right? It changes according to this rate. So kilohertz per Kelvin, right? So this is natural data for an experiment, right? So if you do the ODMR at zero field splitting, at the zero field, sorry, no magnetic field, then you will see a dependence of the dip, right? It is moving, and in this way, basically, you can know what is the temperature of your MB. And again, this is the temperature of a single MB, right? So it is really local, right? You are probing the temperature of an MB is suffering, right? You can do the same for the pressure, so you have a multi-sensor, right? Your MB can detect magnetic fields, temperature, pressure, and also you can detect electric currents and so on. So it's really flexible. Okay, so you can also perform nanoscale NMR. So what I mean with that is that since the MB center is like a tiny dipole, magnetic dipole, right? It will couple with a dipole-dipole coupling to another nearby nuclei or electrons, right? So by doing, no, this is the whole Hamiltonian, it looks complicated. This will be like the dipole-dipole coupling that you have between the spin of the MB and I, that would be a nuclear, right? A nuclear spin. By performing control sequences of the MB, you can select, right, to be in resonance with one of these nuclei, and then you can detect the type and also the distance between the MB and the nuclei. So this is really cool as well. But I didn't want to enter more in the details. Okay, so with that, I will essentially finish this part, right? I think it's fine. Yeah. Okay. So yeah, basically I told you about the MB centers, a bit the hardware of the basically what they are, what are the properties, what we can do with them, right? So they have excellent properties for quantum sensing. There are some protocols for like regressometry, ODMR, nanoscale, and there is also plenty of room for new and improved protocols. And as I told you, this is for like the 3 parts of the talk. Then I have some selected contributions, but I think it is I don't have time for that, so let me skip them. And sorry for that. Okay, so with that, thank you for your attention. Yeah.
Okay, any questions? I have one. You said that depending on the concentration of the different orientations of the MB centers, you can measure the orientation of a magnetic field. But the different orientations of the MB centers can also have different properties for other sensing.
Yeah. Thank you for the question. So basically, so what you are asking is whether, let me go back. Sorry, sorry for the scrolling. If having the different orientation, the different 4 orientation, can be useful for something else rather than magnetometry.
For example, if you want to improve the concentration of one orientation to be better to one, I don't know, type of sensing.
Yeah, exactly. So for magnetometry, in principle, I mean, for many applications, you will prefer to have a single orientation because it will be easier, right? Because everything that you do is typically you assume that you have your MB oriented along one direction, right? And you do the protocol. Whenever you are dealing with single MBs, basically this is what you can do, right? Because you will have one of them, right? And if you want to do ensembles, then there is no way to escape from that, in the sense that you have the 4 orientations. By manufacturing, you can favor one of them, but you cannot completely cancel the rest. So there is always this contribution that sometimes can help you, like in this case, right, for the magnetometry. For other cases, it's typically a problem. So you have like a spurious contribution that you cannot neglect. Right, so
you want to favor
one
orientation, but it doesn't matter what you do.
Exactly. Well, I mean, then depending on the cut of the diamond and so on, you can favor the one that you want, right? Because in principle, they will happen at random. So if you have one, then, well, you need to know what is the direction that you are talking to, because it's where you apply the magnetic field, right? So this is something that you should know. This is a calibration process, yeah.
Thanks, Ricardo, for a nice talk. I know you are not an experimentalist, but do you know how easy it is to create those MB centers like in an ordered way, like to create a lattice or something like that? Is difficult, or I don't know?
Thank you for the question. So for me, it will be extremely difficult because I have no idea, right? But the way in which you do this basically is you have your diamond that you create artificially, and then you bomb with electrons. Basically, try to replace carbon in the lattice, right? And by doing that with a high concentration of nitrogen, then you can be sure that whenever you expel one carbon, one nitrogen will take the place, right? Now, the details of that, I don't really know, but what I know is that this can be done, right? But it still is a challenge. It's a challenge to really have an ordered structure and to produce the MVs exactly where you want. This is a random process, and you do them, right? Basically implantation, and then the next step is to know where they are, right? And this is, yeah, it takes a lot of time to properly know where the location. Yeah.
Yeah, so first of all, thank you for the talk. Regarding the first part of the talk, I have a question because you have derived many error bounds for these quantities in quantum metrology, in which you basically use Fisher information to have some sort of bound. But for that, at some point, you have to assume that the estimators that you use are unbiased. Why is that the case in quantum metrology?
Mm-hmm. Yeah, this is actually a good point. So this, let me put it simple. So this is typically what you do, right? Because if you bias your estimator, right? Well, let's put it this way. You don't want to bias your estimator because essentially what you want to do is that the expectation value of the estimator that you are using essentially brings you to the correct parameter that you want to estimate, right? So if you bias that in a known form, let's say if you know what is your bias, then essentially the same derivation will hold, right? Because adding a bias by hand, let's say, doesn't change anything, right? Fine. Then I know that there are, this can be generalized to unbiased estimators, and in some cases, basically the variance of this Kramer-Rao bound is not like that. It will be modified, exactly. And I think in the classical case, and just from the back of my head, I think you could do better than that, but there is not a guarantee that always will be the case. So I will have to check that, but yeah. Not sure if this answers the question or, yeah? Okay, sorry.
Yeah, and here, thanks for the nice talk. I have a question. In general, when we have a two-level system, we want that the thermal energy is smaller than the difference between the two levels. Why doesn't play a role in NV centers?
Yep. Okay, yeah, thank you for the question. So let me go back to the to this energy structure, like for example here. Right, so you are completely right? So basically what you want, like, I don't know, in trap ions, superconducting circuits, right, is that you cool down the system such a way that basically your thermal equilibrium state is already a pure state, almost, right, to some degree. Here, no, right, because we are starting with a at room temperature, right, so if you compute what is the population of these, basically of all of these states, right, that you have in MV, what you will find, well, this is optical transitions, right? So they are really far away in energy. So you are mainly constrained in these three here, and you will have basically a completely mixed state for that. So at the beginning, so if you don't do anything to your MV, and it's just sitting there at thermal equilibrium 300 kelvins, right? You have a mixed state equally populating the plus and minus and the zero. Fine, this is all you have. Okay, so then the thing is that by doing this optical pumping, you can convert this completely useless state, right, into a pure state, basically accumulate a population in the zero. This is essentially the point. That's why you have this here. This is state preparation. By doing the green laser illumination, you basically you remove the populations from here down here, and then you have the pure state. Yeah.
Hi. Before you talk about Fisher information of coherent states,
yep.
Is the same bound for MV centers as you are using lasers?
Let me go back. Yeah. Okay. So you are asking if is basically this bound holds for MB centers, given that we are using laser, right? Laser and light. Not quite, right? Because in this case, basically, what we have is really like the single frequency mode, right? I'm sorry, the single frequency mode. And this is essentially the one that we are measuring and the one that we are manipulating. In the case of the MBs, we have it's a qubit, right? We have the 3 levels. And then we read it out. And this readout basically is in terms of photons, fine, right? But the efficient information will be codified in terms of the 3 levels of the MB, right? So in a way, basically, the information that you can extract is going to be limited by the 3 levels that you have in your MB, right? I'm not sure if this answers the question more or less, but just in general, let me say that MBs typically operate in the standard quantum limit because it is really hard to entangle many of them, right? And to perform quantum sensing protocols with entangle, basically using quantum entanglement and quantum correlations among different MBs. So yeah, we are typically in the standard quantum limit.
Thank you for the interesting talk. You explained the nice properties of MBs and for the applications for sensing. And I was wondering, for an application for quantum computing, why, or if it's not yet exploited, what are the limitations? Is it the magnetic noise because the qubit is in a magnetic state subject to magnetic noise, or is it the coherence time? But because it's robust to room temperature, you know.
Yeah, exactly. So thank you for the question. Yeah, so being basically like a qubit at room temperature, of course, people thought, can we use this for quantum computing, right? And there have been many proposals in order to use the, well, let me put it like, not sure. Well, I had some slide actually. Sorry for scrolling again. Here, so basically, this is what I wanted to say. So basically, yes, you could use this for quantum computing, but it still is really bad, right? Because the coherence times that you have are in the order of microseconds to milliseconds. These are room temperature, right? So it is way too noisy. Oh, I'm sorry. It is way too noisy in order to perform quantum computations, at least comparable to what we know nowadays in trap ions or superconducting circuits. It's simply, there are many errors, right? And this can be also understood why we are using this for quantum sensors, right? Because quantum sensors, what you want is that it interacts with many things. In quantum computing, it's essentially the other way around. You want a system that is completely isolated, right? So there is a different approach, let's say, right? Still, if you go to low temperatures in the diamond, then the coherence properties will improve, right? So you will get better times. But then, in a way, you are losing the main motivation of using MB centers in the first place, that they work at their room temperature. So yeah, there is a nice thing for quantum computation is that the MBs, right? So the MBs, they cohere fast, no? They have the microsecond times, but you can use the nearby nuclei to store the information. And some proposals, they were like that. So basically, you use MBs like a communication qubit, and then you do computations with the nuclei spins. But still, this is way too more complicated than other approaches. So yeah, but still, yeah, let's see in the future.
Any other question? If not, let's thank the speaker again.
Thank you.
And I think it's time for the coffee break. I want to remind you that this evening is the poster session, so please hang your posters now in this coffee break or in the lunch break, and you have to remove them when the poster session finish today. Okay, thank you.
Muchas gracias. Me alegro. De tiempo bien, ¿no? Sí, vale.